Hello, students. For the last lecture, we considered the definition of limit and how that process allowed us to understand the arithmetic behind the limiting process. That is, x approaching a number and then the function approaching a particular value. And what we've noticed is that that value that f of x approaches is indeed unique. So there are things about the definition of limit that are very useful and help us to understand why this particular definition was created. It's like when the definition of function was finally written down, mathematics proceeded in a very positive way to build and become easier for the population to use. When we have a language set up in any field, we can communicate better. And so the language of mathematics was greatly improved when certain objects were defined. And then a lot of the Europeans got together and defined limiting processes, defined derivative as a limit, defined the Riemann integral as a limit. And so our understanding of the calculus improved greatly. And today, as we study calculus, we certainly are rewarded by all of the work that was done to make our lives easier and the calculus more accessible to us. Now, in this section, what I'd like to do are several examples based upon the homework that give you practice utilizing some of the theoretical results from the definition of limit. There's quite a bit of theory, and as you look in the lecture notes, lots of work there. I want you to go through that, and I will talk about some of that, but we could probably spend a couple of weeks just on the theoretical ramifications of the definition of limit and still not get bored, but we certainly don't have that much time. So what I want to do is start by looking at some examples that utilize the results. And what you're going to find is that when it comes to computing limits, a lot of our intuition is very useful. For instance, when we started the first example before, we found that when we substituted a particular value that x was approaching, we got an indeterminate form, 0 over 0. However, when we look at a limit and we do a direct substitution and we find that the result is a real number, there's a very nice, phenomenon occurring. And that is the phenomenon of continuity. Okay, as long as we're dealing with functions that are well behaved. Now, of course, we can create some really odd functions that will break that rule. But when we're dealing with polynomials, radicals, trigonometric functions, rational functions, when we can do the direct substitution process for a limit and we achieve a real number, then we have achieved the limit. And again, that is the phenomenon of continuity, which we will address more in the next lecture. So what I'd like to do is do some examples and give you some fundamental constructs that will help you to compute limits. But again, never forget your intuition. Your intuition will always be a good source of strategy when you have to interact with these limits. Now, let's look at the first one. So we have the limit as x approaches 2 of x cubed minus 8 divided by x minus 2. We've already seen an example like this before, like I spoke of when we saw the indeterminate form with the example with the radical when we performed the conjugate method. And we're going to do that again. Now, what was going on in that process? It was a means of replacing the given function with an equivalent expression, basically an identity. So if we look at this particular example, x is approaching 2, we can see that we get the same indeterminacy. That is, x approaches 2, the denominator approaches 0, and so does the numerator. Well, direct substitution basically gives us 0 over 0. So we can write here indeterminate. Now, we always need to analyze what's going on in this method because we don't always have the possibility of quote unquote fixing the problem. We may just have infinite. For instance, we may have what we call the infinite limit where the function is unbounded. But I will say this, and we're going to talk about this proposition. If a limit exists as x approaches a particular real number, then we can actually bound the function in an interval about that real number. So we can control the size of the function. So when an actual limit exists, the function must be somewhat well behaved, as long as we can approach the c from either side in a continuous manner. So don't discount the existence of a limit. It's actually a really good quality to have. So now what we want to do is utilize some of our college algebra. So I want to do a sidebar first. Let me just do it down here so I don't interrupt the flow of the problem. So if we're thinking about the fact that we possibly have a function with a hole in it, this is your theorem from your text 1.7 that basically is termed the replacement theorem. And so since x is never equal to 2, and we, for instance, can hopefully determine through some type of an identity that the function is equivalent to another function that is defined it to, then we'll have the limit easily. So again, just remember, if we can replace the function with an equivalent function that makes sense at x equal 2, then we've hit the jackpot. And again, the proof is simple because, again, we never actually equal 2. And so whatever replacement function we have, it simply replaces this function in the definition of limit, and your proof goes through very easily. So let's look at the numerator, which is the key. This, if you recall, and let's write it in a more suggestive way, is a difference of 2 cubes. So this is a formula that you actually learn in college algebra that is very handy. And again, it is an identity. So let me write that identity here. I'll just write it in uppercase letters. A cubed minus B cubed equals A minus B times A squared plus AB plus B squared. So when you take pre-cal and college algebra, this is one of your handy formulas for solving equations, but we don't always remember everything we need as we move to new courses. So now we can simply replace A with X, and we can replace B with 2. So let's fill that in. So that gives us X minus 2. And then, and let me just do this. Let me just say A equals X, B equals 2. So that's kind of our game plan right there. And so now A squared is X squared. AB is 2 times X. And B squared is just 2 squared, which is 4. And so now we can see that this is actually kind of nice because the problem factor will absorb. So this implies that x cubed minus 8 divided by x minus 2 gives us x minus 2 over x squared plus 2x plus 4 divided by x minus 2. And again, we don't want to use slash lines because that's really not very professional. So what we can do is just use some boxes or not use anything at all, because you can see that as long as x is not equal to 2, these absorb each other. That is, they have no impact on the function. So what we can do is simply replace the given quotient with this second degree polynomial. So now, since x does not equal 2, we have x squared plus 2x plus 4. So in the parlance of the theorem, basically what we have is f of x equals x cubed minus 8 over x minus 2, and g of x is the replacement function, which is x squared plus 2x plus 4, and we can just write replacement function. Like I say, the theory can get somewhat tedious at times, and so it's good to look at how the theory actually helps us move the problems forward, and then we can back up and look at some of the arithmetic and feel comfortable that what we're doing is indeed correct. So now let's use the replacement function. So x does not equal 2, so now equivalently by this identity, we can simply do our replacement x squared plus 2x plus 4. And now we're back to the theorem and actually to more intuition. As you look in your notes, polynomials have limits by direct evaluation. That is, again, we can look at the theory, and from the theory, we easily see that direct evaluation is a way to compute the limits of polynomials. Again, we'll look at an example that utilizes some of the algebra of limits, and they kind of roll off the tongue. That is, we can have the existence of two limits and say the limit of a sum is the sum of limits, the limit of a product is the product of limits, and the limit of a quotient is the quotient of limits, as long as all of these processes make arithmetic sense. So what you're thinking of in polynomials is we have powers of x. That's an inductive procedure. But that's one of the nice things about calculus is that by that phenomenon of continuity, we get that flow into the direct substitution. So at this point, we can simply replace x with 2. Sometimes we get some very simple results because the theory is so refined. And then, of course, now what we have is 4 plus 4 plus 4, which is 3 copies of 4, which gives us 12. So when we think about the process of computing limits, your intuition plays a large role. If you think about it with functions that we understand well, like polynomials, direct substitution will give us the answer. If we look at a rational function, ladies and gentlemen, then we have the possibility of singularities, as we say, zeros in the denominator, zeros in the numerator. Now, of course, if it were the case that we just had the 0 isolated in the denominator, that would be an unbounded situation, which is going to be something we study soon, called the infinite limit. But when we can uncover what we call the 0 over 0 or indeterminate form, then there's a possibility that we can repair this. So indeed, what we see here is this is a function with a whole limit. Okay, so we see that the function mirrors this quadratic here. But at 2, the function is undefined. So if we were to mark the point 2, 12 on the graph, we would have a circle or a hole. That is, the function is not defined there, but away from the point 0, 2, all other points on the graph are clearly there, marked by this particular quadratic function. So again, think of your college algebra, your pre-calculus, how that blends into the computation of a limit. And so when we think about functions like this, we can also go back to our college algebra and say, well, why don't we just do synthetic division? And when you do your synthetic division or your polynomial long division, you get exactly this. But we were able to effect that division process by using a very important identity here. So if you forgot this identity and you said, well, I'm just going to divide the polynomials and see what I get, you would get the same answer. So don't think that a particular technique is the only way to compute a limit. There are many ways to go about computing limits, just like there are many ways to solve equations. So you can put your own signature on the problems. Just make sure that as you work through the problems, you're using good techniques. Okay, let's look at another one. Now, the next problem, again, I'm trying to appeal to your understanding of your prerequisites, because let's face it, if you're running out of time on the test, you're going to check that direct substitution first. Well, that's what you're always going to do, especially if you have functions that you understand, that you've been studying since Algebra 2 and college algebra. And what you're going to look for, again, is that indeterminacy. And then keep your fingers crossed that you can find the replacement function. So here's another example. We have the limit as x approaches 3 of 3x squared minus 11x plus 6. And we have negative 2x squared plus x plus 15. Now what we can see here, and if you want to use, you can use parentheses here if you want. It's certainly not required, but if that makes it look a little better, we can do that. Now, what you can notice here is that when you substitute 3, we get a very interesting situation. Notice we get a 3 plus a 15, which is 18. And then, of course, we get a negative 18 here, clearly 0. And then upstairs, we get a similar situation. We have a negative 33 here. And then with the 3, we have a 6. And here we've got a 3 times a 9. So that gives us a positive 33. And of course, what ensues? Indeterminacy. So we can simply say we have an indeterminate form. So let's just think about this. If you're doing a problem or a limit on a test, either, and it's a more advanced problem, then you're either going to use some type of special limit, which we're going to talk about, sine x over x as x approaches 0, or you're going to be tasked to look for the replacement function. You're going to find the identity that solves the problem. That is the replacement function that is actually defined at 3. So again, you can imagine on the first test that you may have a few limits that will be fairly straightforward, or maybe limits within a more complicated problem that will be very, very straightforward. But then the crux of the problem will be applying this replacement theorem. So if you think about what you've done in your prerequisites, it really sets you up for this. So how nice that the practice that you had preceding this course has actually prepared you to compute limits. So let's do some sidebars here and see what we can get. So let's do sidebars. I like to go ahead and do these and then go back to the proper result and then apply the theory in a way that keeps the work neat. So we can use our AC methods. So 3x squared minus 11x. That's always a nice theorem to prove in pre-cal and college algebra to shore up a very famous lemma by Carl Friedrich Gauss called Gauss' lemma, which basically says, and you may remember this, that a primitive integer polynomial that factors over the rationals also factors over the integers. And then you can actually work in, I've worked in a theorem where you can work in the Z and the W that corresponds to the AC in your coefficients here to find the two numbers that add to the coefficient of the first degree term. So that's actually connected to Gauss's work in algebra. And of course, he was one of the greatest mathematicians who ever lived. So we are still using all these great results that all of these preeminent mathematicians left for us, and we are quite grateful. So now we can look at this and say AC equals 3 times 6. And then when we look at that, we're thinking, okay, well, you know, it's not quite what we need. I mean, when you think about this particular example, you're thinking, okay, well, if I go ahead and add these two numbers, that's not going to give me an 11. So we just get a little bit creative. Let's do a prime factorization of the 6 and get a 2 times 3, and then put the two 3's together to give us a 9 times a 2. And that's almost there. So then we just put in the two negatives. So now we actually have two numbers in product that equal AC. And now we can, and this, of course, in the parlance of the AC lemma, Z equals -9 and W equals -2. So now we can rewrite the middle term. So basically what we're seeing is that this integer polynomial factors into two integer polynomials. And of course, you can also create theorem formulas for this, but this is so easy to do, it's probably quicker just to do it this way. So we have 3x squared minus 9x minus 2x plus 6. And then, of course, factor by grouping. We have a 3x and then an x minus 3 plus a -2, and then, of course, an x minus 3. So this gives us x minus 3 times 3x minus 2. So that gives you a factorization of the numerator. Let's do the same for the denominator. So we have -2x squared plus x plus 15. Now, if you don't like the negative there, and it does kind of get in the way, just go ahead and factor it. So negative 2x squared minus x minus 15. A little bit easier to work with the leading coefficient that's positive, but you do what you like. So there's our -1. I'll write it there so we don't forget it. And now, of course, AC equals 2 times the -15. So this is like the last one, except now we actually do have a negative AC. So we're only going to end up with one negative. But of course, this is, if we do the prime factorization in the 3 times the 5, we can just pair the 3 with the 2 to give us a 6. And then, of course, move the 6 or the negative with the 6 and still maintain the product. But now that we have two numbers whose sum is actually -1. So that's good. So here we'll say Z equals -6, and we'll have W equals 5. Now, of course, it doesn't matter how you assign these. Clearly, if it did, this wouldn't be worth anything. So now we can do it. So we have 2x squared minus 6x plus 5x minus a 15. -1. So now we can factor by grouping 2x, x minus 3, plus 5 times x minus 3. So this gives us the negative of 2x plus 5 times x minus 3. Now, of course, this is really good when you think about it, because when you look at this, you're seeing that we'll have the terms absorbed, which are giving us the problem to begin with. So now what we can do, I'll just go ahead and move the problem down here. So we have the limit as x approaches 3 of 3x squared minus 11x plus 6 divided by -2x squared plus x plus 15. I think it's always good to do your calculations and then go back to the proper problem, like when we do integrals and derivative problems. We want to make sure that our work is clean and good. So now, again, we can use some properties. So we have the limit as x approaches 3. Of course, replacement theorem says we can now use in the numerator x minus 3, 3x minus 2. And in the denominator, of course, we have our negative. Don't forget that. We have a negative 2x plus 5 and x minus 3. So now, of course, since x does not equal 3, these terms absorb. So our replacement theorem now, if you want to write it in terms of the last, we would say g of x, and don't forget the negative there, will be the negative of 3x minus 2 divided by 2x plus 5. So you can just move the negative upstairs. So this is the so-called replacement function, a function that is equivalent to the given function away from 3. So again, we have a function with a hole in it, which is always going to be the case when we use this theorem. So now one thing that you will find at this point, you're thinking, well, now we can just do direct substitution. And you don't really have to worry about the negatives. So if you, however, want to think about some of the limit theorems, you can always extract negatives. Okay, so constants like a -1 or anything can always be extracted from the limiting construct because they are independent of the variable x. So if you want to go ahead and remove that and do your direct substitution, that's fine. So in this case, you could say, well, we have the limit of a quotient, so that's the quotient of limits. So we'll take our negative. Just to practice a little bit, direct substitution ends up doing it all. But I just want to give you some practice writing the actual theorems. So if you want to get creative, if you start to tutor someone, you can say we'll use the quotient rule, or you can just say we've got a rational function, so we can just do it by direct substitution. Any way you want to do that will be fine. So once you've gotten to this point, at this point, you can work or finish the problem as you like. Just make sure that your notation is good. So now we have the negative out here, and we just do our direct substitution. So we have 3 times 3 minus 2. And then downstairs, we have 2 times 3 plus a 5. So this will give us the negative 9 minus 2 is a 7. And then, of course, we have a 6 plus 5. So this gives us -7 over 11. So now what we see, again, we have a function with a hole in it. Now, what's important here is the craft of doing the algebra, okay? I don't want to see a lot of chicken scratch and just hit and miss kind of factoring. I want to, when I teach my college algebra kids and pre-calculus kids, we cover factoring methods, the AC method like this. And so I want to see this process because it's important, because as we move through calculus, we will be forced to do lots of factoring to clean up expressions so we can analyze them, just like you did when you did theory of equations in college algebra and pre-calc, and especially trigonometry. If we throw that out, then our precision is gone, and we don't want that. We want our work to be precise. So now we have a good example, and of course, these would make great test questions. Okay, let's look at another. We got several examples to do, but that's good. Now, what I would like to do is just mention some special limits. And if you look in the notes, the special limits require the use of the squeeze theorem. And I may make another video and say something about some of those ideas. They're very intuitive, but I don't want to bombard you with over amounts of theory until you get comfortable with utilizing the results, and then we can back up and say a little bit more about those. Special limits that don't admit to the replacement theorem. You can think when you utilize trigonometric functions, you think how the sine function was defined. It's defined as the y-coordinate of the unit circle, where we consider the input to be the distance along the unit circle or the corresponding angle. That's not very helpful geometrically. I mean, geometrically, it's very helpful, but it's not very helpful arithmetically. We're like, okay, so what do we do with sine? And what we're going to find as we move into calculus 2 is that we will be able to write a power series for sine, for the trig function, sine and cosine, tangent, all of them. We'll focus on sine and cosine. And you're thinking, wow, that arithmetic realization of those functions will now create an object that our calculator can evaluate. Because we can't just look at a unit circle and say, well, sine of 1 radian equals this. That's not arithmetic. So the calculus is what pushed forward the invention of the power series, which then made all of these functions arithmetic, which now actually makes sense as to how your calculator works. And we'll say more about that as we go along. So one of the special limits looks like this. The limit as x approaches 0 of sine x over x divided by x. Now you look at that and say that's 0 over 0. But this is actually a function with a whole limit, because away from 0, this function is defined. And the answer is actually 1. Later on, when you do discuss the infinite series in calculus 2, we will see that those results are consistent with this result. So I'm not pulling your leg. Very interesting result, don't you think? And the other one is the limit as x approaches 0 of 1 minus cosine x divided by x, that equals 0. Well, again, when you look at this, if you let x approach 0, well, the denominator is 0 and the numerator is 1 minus 1. But, you know, it's like, well, okay, that's 0 over 0. So what do I do with that? We don't have any replacements for cosine except other trig functions. So when you think about it, if we can't replace cosine with a power series yet, then we really don't have any avenue to prove this. And like I said before, this requires the utilization of the squeeze theorem to get this, and then we can cheat to get this. Let me show you, at least now, because this is right along the lines of how we've been doing the previous problems. So let's look at this and see if by knowing 1, we can actually get 2. Let me show you. So we'll just say we can prove 2 using 1. So let's do it. And of course, it's going to be the conjugate technique, which I've already talked about in the first lecture. So don't be afraid of doing the conjugate technique as you work through this. So now we start out with this, and then we just realize that this is just 0 over 0. It's indeterminate. So now we're going to use our conjugate technique because we like it, and you know it's certainly an avenue to utilize. See what we get. So we get 1 minus cosine x divided by x, and then we of course multiply by the conjugate of the numerator upstairs and downstairs. Okay, so this is the technique. Again, you think, oh, we're using an identity. I mean, think about it. We're using a unique construction of one. We're not changing the function as to value, but we are rewriting its structure. Because just like we use the technique of adding and subtracting when you complete the square in your algebra classes, and we'll do the same in calculus, you are refining the function. You're rewriting it so that you can utilize other algebraic constructs. So adding zero in a convenient way can be very, very useful, like multiplying by one in a convenient way can be very, very useful. So now we're looking at the limit of this object. So now we can use some of our basic trigonometry. So notice, of course, upstairs, we just have a difference of two squares. So this is just going to be what? 1 minus cosine squared. The outer and inner terms by the distributive law absorb. So this gives us 1 minus cosine squared x, very simple. And then we have x times 1 plus cosine x. Again, just using simple trigonometry. Okay, we're still in trouble. We didn't improve anything, but now, of course, when we look at this, 1 minus cosine squared defines the square of the sine. So we get sine squared x divided by x times 1 plus cosine x. This is what I'm talking about, utilizing what you know within the construct of the limit theory to move problems forward. Now, we have a very important result, which I mentioned before. That is, if you have the existence of two limits, then the limit of the product of those functions can now be the product of the limits. Let me say that again. If you have two limits existing, and you take those functions and you multiply them, that is, as x is approaching the same number, then you can simply take the product of the two respective limits. Again, that's just like I said before, with the limit of the sum being the sum of limits and the limit of the quotient being the quotient of limits. Very, very important results. And of course, this rule that we're going to use right now, if you look in the notes, has a very elegant proof, but it is by no means simple. But once you understand the flow of the arithmetic, it's not so bad. So let's do the algebra. Sine squared is just sine times sine. So we have limit as x approaches 0 of sine x, and I'll put a little dot here to emphasize the multiplication. And downstairs, I'll do the same thing, even though it's not required. I just want to make sure that you're seeing the multiplication. Now, what we can do to use the product rule, so to speak, for limits is just kind of section these off. We can look at that as one function, and we can look at this one as the second factor function right here. So now we have the limit of a product of two functions. Now, we go out on a limb and say, okay, let's break that up into the product of limits and then keep our fingers crossed that those two limits actually exist. Because if they do, then we've worked the theorem backwards and we have a correct result. So now we'll say product theorem. So this gives us the limit as x approaches 0 of the first product, or the first function, sine x over x, times the limit as x approaches 0 of the second function, sine x over 1 plus cosine x. Now, we're at the same point as we were before, but notice we know this limit exists, and we know this limit exists by direct substitution. You could do the quotient rule, or you can just substitute 0, and you get sine of 0 divided by 1 plus cosine of 0, which is well defined. So I'm not worried about the fact that you can say, okay, well, if I do direct substitution and I'm working with sines and polynomials and things like that, I'm good because the result allows me to do that. But what's really important here is that this is a significant result. So if we can claim this result, then we have this limit directly. So now we can say 1 times, and then we'll do our direct substitution, sine of 0 divided by 1 plus cosine of 0. So that's 1. And then, of course, sine of 0 is 0. Cosine of 0 is 1. So we have 1 plus 1. So we have 1 times 0 over 2. And this is 1 times 0, which indeed is 0. So our proof is valid. And this is what I wanted to do with some of these examples. So you can see all of these results as we work through these limits. And then you can appreciate the results. Oftentimes in mathematics, you can prove something and then say, well, that's an interesting result. What can I do with it? Okay. So what I tend to do is to focus on the theory enough that it undergirds what I'm about to do in a problem. And then we can securely say, wow, okay, yes, this is a significant result. So if we look at this problem, we can see this as being a very significant way to compute limits. There'll be many times where we will have many terms, and then we can section the terms into functions that we understand, as we've done here, and then apply the theorem as we've done here and move it forward. Lots of authors will say, okay, throw caution to the wind and work it forward, and be hopeful that what you see at the end of the problem is something you understand. That is much better than just being stymied and saying, I'm not sure. No, see, that approach will never help. That approach will never work. You've got to practice and study enough so that you have the confidence just to go out on the board, jump into the deep end, and swim to the shallow end. That's what we did with this problem. So again, the practice will give you the confidence to say, okay, well, if I'm going to solve this limit, I can't just stare at it and hope for the best. I move it forward. So that's really how you do the calculus. You think about proving a theorem. You state a theorem, you assume it's true, and work it. You don't sit there and think, I wonder if this is even true at all. I'm not going to do that to you, and we're certainly not going to spend time working on worthless results. Okay, very good. This is a great result. Now, if we know, for instance, and I want to look at an example here that utilizes the first result so that you can see how things will work. And I've got an example here. I think I'll make this work nicely. So here's an example. That first result, sine x over x as x approaches 0, basically means that the argument of sine and what's in the denominator must coincide. As long as these two expressions go to 0 as x passes to 0, then we can apply the result. So let me give you an example which is a little bit different from what we just did. And then you're going to say, oh, I get this. This makes perfect sense. So say we had something like this. Let's just say that A and B, element of R, and we'll say are fixed and non-zero. So we want to do like a more generalized result. So you could think of A as being 2 and B as being 3, any number, but not 0. Okay. So, and when we say fixed, what does that mean? That means constant. They're fixed, so constants. That's a very common expression in math. We'll say fix A, fix X, fix epsilon, if that's going to help us move the problem forward. So now we can actually compute the following results. So we'll say compute the limit. So we'll say X approaches 0 of sine of AX, and I'll use parentheses here, even though we don't need them. I don't want you to think I'm just being sloppy, but yeah, it's a product, so it's unambiguous, but we'll just do that. Say you just have sine AX divided by sine BX. This will be an algorithm that you can use in many examples if you see this on a test. This is a common construct in the calculus. So again, when you look at this, you've got sine AX, replace X with 0. So you have sine of 0 upstairs, sine of 0 downstairs. And you think, well, here we go again. Indeterminate. So just write that down, indeterminate. So the only thing we have is the special limit. So just like we did before, we can multiply by a convenient 1. Now, one thing that you will notice using the composition result, let me just do a little sidebar here. Limits of compositions make sense as long as we can move the limiting process inside to the inner function. If we can do that, and the result of applying the outer function is a real number, this is a limit 1.5 in your text. If the result of applying the outer function is a real number, then we're done. And that occurs more than you might think. Again, that's the process of limit. And then as we move into continuity, we'll just say, okay, limits and continuity are basically the same thing. There's only one little tweak. So then we'll start saying by continuity. Before that, we say by the limit theorem, but it really doesn't matter. Continuity is just a little bit more useful because it starts to take over once we finally define it. So the sidebar looks like this. For instance, we know that this limit do a sidebar of the sidebar is 1. So what about the following? So we can now do this. We can say sine, let's write a composition. So we're just going to flip this, -1. Limit as X approaches 0. Now, this is just the limit of X over sine X. But we know that the limit of the inner function is 1. If we pass the limit inside, and then we can reciprocate 1 and get 1. Well, that's good because 1 is a real number. So this will just be, by the composition result, the limit as X approaches 0 of sine X over X to the -1, which is just 1 to the -1, which is 1. But no, observe. By definition, sine X over X to the -1 is just X over sine X. Okay? So, if the limit of sine X over X is X approaches 0 is 1, then that's also the limit here. So what we have is if and only if, just writing it this way so it looks more like this problem. We've just proven that using a composition. And that has to make sense. That has to make sense. If a function is approaching 1 as x approaches 0, then its reciprocal has to do the same thing. Because we know if we reciprocate values that are approaching 1, we get the same thing. There's no difference there. So the beauty of the composition result is that now we can apply this sidebar to this problem. But we have to make a few adjustments because A and B are just non-zero numbers. So we can't just throw caution to the wind and stick X downstairs. So how are we going to fix it? Well, first thing we're going to do, this is a really neat problem. First thing we're going to do is we're going to break it up into 2 pieces. We're going to say sine of AX. Well, I left out the X. Let me stick that in. Sine of AX times 1 over sine of BX. And now you're thinking, well, we need AX downstairs because, of course, if X approaches 0, AX approaches 0. So we'll just say X approaches 0 if and only if AX approaches 0, and X approaches 0 if and only if BX approaches 0. Nothing, the constant's not going to make any difference. It's still going to 0 if X is, because the constant has no dependence on X. So this now says we need an AX here and we need a BX here. So let's go to the next step. So the limit as X approaches 0 of sine. So this is the smoke and mirrors that we need. So let's put this AX and then to fix the other one, we need a BX. We know that the argument of the sine must be replicated in the denominator here and the numerator here. So now when we look at this, if we're thinking products, again, I'll write that. If we're thinking of products, we would know what these would approach almost, because we're not quite there. So we need an adjustment. That is, we have to absorb the A here by multiplying by A and absorb the B here by dividing by A. And now this is an equivalent expression. So this equals this. X is not equal to 0. It's approaching 0. This equals this. And so now we can apply the limit theorems. Note, this is just a constant by construction. So let's take the problem down here. So this constant can be extracted. Constants can always be extracted with limits. And now we have the limit of a product is the product of limits. Elegant problem, very nice problem. Now you could do a change of variable, but you don't need to. We have this construction here that says if X is approaching 0, so does AX. If AX is approaching 0, so does X. They go in both directions. So now we have the limit of a product is the product of limits. And we just got this result from the first sidebar. So now, both of these limits we know are 1, 1, 1. Again, the numerator has the argument of the sine going to 0 and the denominator. And the second one, we have the argument of the sine going to 0 and the numerator going to 0. So this will now be A over B, special limit times 1, times 1. That's just A over B times 1, since 1 times 1 is 1. And that gives us A over B, the multiplicative identity. So you're thinking it wouldn't be too hard to remember this result, would it? Because if you have this, the answer is just the ratio of the what? The coefficients of X, A over B. Amazing. Not really surprising when you think about this, but what this particular result requires, again, is the special limit that we started with, and then utilizing the composition. So how does the limit of a composition work? You've got this composition, okay, and you go out on a limb. You move the limiting process inside. That is, you know the limit of the inner function. And the outer function makes sense at that limit. That's basically the limit of the composition result. So when we do that, and it is an extremely important result, where you move the limiting process into the inner function, and then compute that limit, and then apply the outer function, just like we did here. And that gives you a very, very useful result. We often use that result, ladies and gentlemen, without even thinking about it, like, you know, it just seems so intuitive. But I think it's really nice when you can find an interesting result using a special limit. And now you can apply this technique. If we had another trig function hanging out, we could just do it again. You just have to offset. You just have to offset the what? The coefficients. And you have to make sure that, again, if we had another trig function, in this particular case, it would have to stand on its own. We couldn't do another x because then the x's would be out of balance. So you can see the technique of multiplying by x over x, and then, of course, with the coefficients, the a and the b, and then repairing that here. This is equivalent to this. So this technique you will use quite often. And I think this is really important when it comes to analytical methods. As I often say, now we need to use some smoke and mirrors. And my students last semester would say, well, I need the smoke and mirrors for this. I'm not sure what to do. And so once you have that particular strategy, it comes back over and over. You don't have to worry about it, because you can rest assured that you will use techniques like this throughout the calculus sequence. Now, like I said before, where you use the limit theorems in the abstract, those are really simple, okay? That's just applying the result. If you're not given much information and you've got to do the limit of a quotient, then you just apply the limit in the numerator and denominator and use the given numbers and plug them in, so to speak, substitute them. Those are trivial. But the problems that have the expressions are most important. Now, I want to do one more limit, and then I want to do a difference quotient, which is actually going to be the definition of derivative that I tend to use more in this course than most professors, because when it comes to proving results, we need a mechanism that gives us a nice answer. But before we do that, I want you to look at one more limit example, and then we'll look at the difference quotient. So we have the limit as x approaches 9 of 3 minus the square root of x. And then we have x minus 9. So what I thought I'd do was just dress this up a little bit so you can still get more work utilizing the replacement theorem. Now, here's the thing. Don't discount your ability to factor, and don't make it up either, okay? If you factor something, then check to make sure that it works, okay? Check to see, okay, did I do this right? You know, we use the AC method. One thing about the AC method is that you've got to have all the numbers right, and once you have the numbers right and factor it and everything runs through perfectly, then that's kind of your check, where you've got the same term repeating so you can factor in the final step. It's a self-correcting mechanism, all right? So that checks itself. But what we can see here is that when you replace x with 9, you get the same thing. You get this indeterminacy. Indeterminate. And let's face it, these are the most interesting problems. And when you do your physics and you do your engineering and all that, these come up over and over. The division by zero, the indeterminate form, it was made for calculus. So now when you look at this, you're thinking, well, you know, I can factor this. So the first thing we want to notice, and I'm going to go ahead and apply this, is we've got the x minus 9 downstairs, which we can factor, and then we have the radical upstairs. So let's go ahead and just factor a negative. So we'll have the limit. Just do a little bit of work before we do our sidebar. So we have the negative of the square root of x minus 3 divided by x minus 9. And now this is so simple, we don't really even need a sidebar. I kind of save this for later in the lecture so that now when it's not so difficult, you don't have to really break apart from the problem, but certainly always do if you want to build your confidence. So now what we can think of this is as a difference of two squares. So let's do that. Let's write it in a convenient way. Now, of course, the negative, since we just maybe want to use some of our properties, our limits, let's go ahead and factor the negative, which we can do with limits. We're going to find the same property of linearity with the derivative and the Riemann integral. So we can factor constants. The limit of a sum is the sum of limits. The limit of the derivative of a sum is the sum of derivatives. We don't get the product rule in derivatives, unfortunately, but we will certainly find its use later on as we move through the course. So now we get the negative of the limit as x approaches 9 of the square root of x minus 3. And now downstairs, what we want to do is write x as the square root of x quantity squared and write 9 as 3 squared, okay? And you probably did something like this in your pre-calculus class, but unfortunately, by the time you get to the end, you've left a lot of the algebra behind because you're doing induction and the binomial theorem, and it starts to fade. So we have the negative of the limit as x approaches 9 of the square root of x minus 3. And of course, that's the key here. We factor the difference of two squares, so we have the square root of x minus 3 and the square root of x plus 3, okay? And so now, of course, we have a replacement theorem, the root x minus 3 absorb, as they say, and that leaves us with the negative of the limit as x approaches 9 of 1 divided by the square root of x plus a 3. So now when you look at that, you're thinking, well, I'm home free. I mean, that, you know, I don't even have to do the limit of a quotient. You know, the limit of a constant, of course, is said constant. You have to believe that, right? I mean, we talked about that in the first lecture. I mean, if there's no dependence on the variable, then it's not going to change. I mean, that's one thing about limits. You can't just make it up. You have to use good sense and the theory. And many times when you apply that good sense process, you get the right answer. So now we've got what? The negative, I'll put a -1, and then we just do direct substitution 1, square root of 9 plus 3. So this gives us the negative of 1, and the square root of 9 is 3, so 3 plus 3. So we just get -1/6. So what's interesting about this particular problem is that it's just like what we've been doing. And I want you to get comfortable with this. I want you to get comfortable. You can even make up your own problems when you think about it. Just remember that when we're dealing with trig functions, we're dealing with algebraic functions, we're dealing with rational functions, polynomials, things of that nature, we can actually evaluate limits by direct substitution as long as the result is a real number. That is something that you find in all the theoretical results in this section. It turns out that most limits are just computed by direct substitution. And that's a plus. But you would think that limits would be easier, and they are really not easy. Because when it seems simple, you think you aren't doing enough work. And then when you don't do enough work, you don't finish the problem to completion. So just remember, however you attack your result, once you apply the theorem, then like here, once we said, okay, we're ready for direct substitution, boom, we do it. The notation supports all of that. So I want to make sure that your notation is good, because when you test, you'll write your mathematics down and you're going to scan it and upload that to Blackboard so I can see your work. Okay? So now let's look at an example of a difference quotient. So this is something from your homework that I thought was kind of interesting. We have a position function, S of t, and I'm going to write this using fractions. We have 49 over 10. That's negative 4.9, but I just wrote it with a fraction, t squared, because it's just nicer, plus 300. Now, when you do physics, position function derivatives give you the velocity, but that'll come later. So right now, basically what we want to do in this example is define S prime of t, and when we get to this, this will make more sense, but this is going to be the derivative, but it's actually going to be a limit. We're going to say that this is the limit as, in this case, of course, I'm a creature of habit, I need to write a t here, and we're going to take a to be a positive number, like a time. So we're going to say t approaches a, so we'll say a is positive, and in this case, we'll look at this as seconds, and we will define S of t in meters. And so this will be the limit. And I'm going to flip this around. They invert this for some reason. It's not necessary. So this is going to be S of t minus S of a divided by t minus a. And this is actually going to be an alternative form of the derivative. We'll say much more about this. There'll be two forms that will be used, but this alternative form is actually much more powerful, and I tend to use it, and I want you to understand it. So now, basically what we want to do is compute. Let's just pick a particular value of a. You could do it like it is if you want, but we'll just do this. We'll just say S prime, I think what I did here, of 3. So this would be limit. Of course, you could do this in general, but I'm not asking you to do that now. Later on, you could do that. So t is approaching 3. S of t minus S of 3 divided by t minus 3. It's kind of a nice example if you just do it in general. But since this is something kind of new, which I haven't defined, we're just looking at this as computing a limit, and that's all. Okay, so it is actually going to be a velocity, but we're just going to compute a limit. So now let's fill everything in. So now we have S of t, which is up here, minus 49 over 10, t squared, plus 300, minus, and our S of 3. So we have 49 over 10, and of course we've got t squared, so that's times 9, plus 300. And then downstairs we just have t minus 3. Now, of course, the 300s absorb. And now, of course, if you want, and of course, let me not be so sloppy here. We got a minus right there. Okay. And so now what we can do is just go ahead and factor the negative 49 over 10 and retain the minus here. So let's do that. So now let's go ahead and just factor, just take this outside. Take both of these outside. They're common to both. So we get negative 49 over 10 limit as t approaches 3. And we're left with, in this particular case, we've got t squared minus 9 over t minus 3. So how nice. Not all problems are this simple, but I thought this was an interesting problem because your author introduces the concept of derivative in advance just to give you some practice with it. We'll spend lots of time with this. So now this will be negative 49 over 10. And of course, this is a function with a whole limit. This will just be t minus 3, t plus 3, t minus 3. So now when we look at this, the definition of derivative is indeterminate. We start out with indeterminate. It's like, man, that's crazy, but it makes sense when you think about what a derivative is. You know, you are actually computing the slope of a tangent, okay? And so the tangent will only intersect the curve at one point. So you got the secant line, which intersects at 2, and then what happens is that as the point converges to the other point, or as the distance between those 2 points on the x-axis or t-axis come together, that is, as t approaches a, or delta x approaches 0, or whatever variable you want, if the tangent line exists, then it will only intersect the curve at one point. And we'll say lots about that. So you're thinking, man, how do we get all this theory out of something that starts out indeterminate? Well, it's amazing. So now the t minus 3, they both absorb. And so now you've got, wow, I got the easiest limit in the world. That's just a polynomial in t, the limit as t approaches 3 of t plus 3. But now, of course, that's just direct substitution. So we get negative 49 over 10 times 3 plus 3. So this is negative 49 over 10. And then, of course, 6 is just what, 2 times 3? And while we're at it, I was thinking, let's go ahead and write the 10 is 2 times 5. And then, of course, absorb. So that'll be what? A negative 147 over 5 meters per second. So this is an interesting problem. You're thinking, well, it's fairly simple position function. And we did this for a particular value. So what I might ask you to do, why don't you just try it for A? Just do it in general and see what you get. And then substitute the value of A as 3 and see that you get the same thing. That would be a nice exercise. But I thought it was interesting. You can choose either way. You can just do it specifically, or you could do it more in the abstract. So look to see what the function would be in terms of A. We're just computing it this way. That might be a neat exercise to do. Okay. Now, the very last thing that I want to do is talk about a result that has to do with the boundedness of a function. And I think I said it over here somewhere. I think, let's see, I promise I didn't swallow it. Let's see here. Oh, here we go. Here we go. Now, like I said before, there are lots of theoretical results in this section, and I will say some more things about them, but I want you to be comfortable with the results and utilize the algebra, because you can't move forward if your algebra is not up to par, okay? And the arithmetic from the first section is going to keep you more than busy. So here's what I want to show you that is very interesting one of the very neat results. This is not formally stated in your book, but what's interesting about it is that if you want to prove the product rule for limits, you really need it. You can't get away from it. So this is what I said before. So I'm trying to kind of bring out some of the theory piecemeal so that you get theory maybe in smaller doses and feel more comfortable with the results. So when you look at this, limits are unique real numbers. We know this. And if you want to think about trying to prove that, you may have a little tough time with it, but it's actually very doable. And I'll say more about it. I'll give you time to think about it. I mean, clearly, from what we've been doing, if they weren't unique, we wouldn't have all these nice theoretical results. So if we fix a C, X is approaching C. So we look at this and we say F has a limit L as X approaches C. So we're saying that our function behaves well at C. So as X approaches C, we get a real number. We call it L. Then there exists a delta greater than 0 and a B greater than 0 such that the function is bounded. That is, the absolute value of F is less than B. If we are in a delta neighborhood about C, but of course we don't really know what's happening at C, we have to kind of kick that out, but maybe it's not even defined. We don't know that. Remember, when we do the limit definition, we exclude X equals C, because we have the 0 less than the absolute value of X minus C less than delta. So we are not requiring that the function even be defined at what? C. That's very important. So when I write this, I'm saying that may not be in the picture, so I have to make sure I kick it out. So as we approach C from either side, the value of the function is bounded. It can't get crazy because this limit exists. You can't just, you're approaching a finite value and then you hiccup and you're at infinity and then you drop back down. That's not going to happen. The function's well behaved. Why is that? Why is that? And this is actually simpler than you might think. What we're going to do, we're going to make the arithmetic a little bit easier, and we're going to specify that the epsilon in the limit definition is 1, okay? We know the limit exists, so what you're going to do is you're going to say, here, Professor Wallace, here's epsilon equal 1, do your magic, and well, the magic's easy, okay? So now, by definition, there exists a delta. Because we know the limit exists, if you give me an epsilon, then I can find a delta. There exists a delta positive such that, in this case, 0 less than X minus C less than delta, which basically is this, X element of C minus delta. We fleshed this out before, C plus delta. And then I'm saying I'm minusing C. It's like we kick out the C, so we take away that element. So we've got like a hole at C. So this, which implies that now f of X minus L is less than 1. Okay, so you give me the epsilon, the limit exists, so I can find the delta. So if X is within delta of C, then f of X is within 1 of L, right? What does this mean? Well, this says now we've got what? -1 less than f of X minus L less than 1, if and only if. This is kind of like what we did before we were doing our estimates. So the estimates I set up in the first lecture really help you do the theorems in this section. But but you got to get used to it. So now we've got what? L minus 1 less than f of x less than L plus 1. So this is where we have to say, okay, I don't know anything about these numbers. I mean, in absolute value, I don't know how big they are. So I mean, I don't know what L is. I know it's a real number. So here's what we're going to do. This is what I did before. Notice, remember, before we had two positive numbers, so it was easy to bound the absolute value. So what we're going to do is set B equal to the maximum of the absolute value of L minus 1 and the absolute value of L plus 1. And that's the key. That's the key to this proof. So then X element of C minus delta, C plus delta, staying away from C, keep that out, implies now that the absolute value of F is actually less than B. Because now when you slap on the absolute values here, the absolute value being an increasing function, so to speak, when we think about this, we look at this and say, okay, well, with that case, if that's the case here, and I'm taking B to be the maximum, then I've got an upper bound for the absolute value. It's kind of like, here's an example of this. Say you have, say, L equal to negative 10. And so we have L minus 1, so that's negative 11 less than f of x less than negative 9. And so now this will imply that the absolute value of f of x, in this case, will be less than 11. Because now what we see is that the larger value in absolute value is here. Okay, so now when we consider the absolute value, that's what this mechanism is doing. So if f of x lives between negative 11 and negative 9, its absolute value will be less than, in this case, 11. So you think of it like this. So negative 11, negative 9, f of x lives in here. And so this mechanism allows you to negotiate the fact that you really don't know what L is. And you can't say, oh, well, this is positive and that's positive or whatever. They could both be negative. Who knows what the distribution is going to be? It just depends on the value of L. And so this is what you need to be able to do to give you the correct result. So I hope this has been helpful in trying to understand that the existence of the limit is a really big deal, because like I said before, there's only one little idea that we need to go from the limit existing to continuity. So the limit is a big deal, and its existence is very important, and it's a great thing to have, because we know if we have the existence of a limit, we can bound the function in that delta neighborhood about C, which is very important. We know that we can control the size of F, okay? So as you continue to work through these examples, think about what the definition of the function is. Think about what that definition gives you theoretically, and work with your algebra to make it clean and effective, because it will definitely pay off. These results will follow us through the entire calculus sequence. So the time you spend now will definitely make a difference. So that's all I have to say. You have a great evening and good luck as you study. We'll see you later.